Hi everybody. Today we're going to be looking at double integrals in polar coordinates. Now if you hear something in the background, please try to unhear that. That's my dog playing with her toys. Alright, so double integrals in polar coordinates. So the one thing that we're going to have to do here really quickly is to recall what we know about polar coordinates. So really quickly, I'm drawing this diagram to show us that every ordered pair in Cartesian can be expressed as r comma theta, which is in polar coordinates. Now, using polar coordinates, we're able to extract a lot of important information. According to my diagram here, we're going to have that x squared plus y squared is equal to r squared. X is equal to r times cosine theta. Y is equal to r times sine theta. Alright, so we're definitely able to extract this using polar coordinates. Now, from Calc 2, we're actually then able to say, hey, if we want the area of a sector bounded between alpha and beta, then we're going to have to use 1/2 r squared d theta. Alright, and this was the area of a sector bounded between two radii. And we got a little bit more general when we did this in Calc 2, where we said, okay, we're going to go from some alpha to some beta, and what if the radii that we're trying to find the area of the sector for is bounded between these two radii? And I'll give you a very quick depiction as to what that looks like. Some x coordinate, some y coordinate here. Now I'm going to bound my function. Let's say this was some function, call it r naught, radii, initial radii. Alright, and I have some other function here, call this r1, and this is all in polar coordinates. And what we're going to do is we're going to go bounded between two different angle measurements. So call this theta 1 and then call this theta 2, or better yet, we can call this alpha and we can call this beta. Now the area of the sector that we're looking at here is going to be this area right in here. And that area of the sector is what this formula was calculating. It said, hey, what you need to do is you need to find the difference between the radii squared and then multiply it by 1/2. It's still the area of the sector, but what it's essentially doing is it's calculating this whole area here, the area bounded by those sectors, and then it's subtracting out this area right in here. So that's what's actually happening here when we're taking this formula, or when we're using this formula here, is it's taking one area and subtracting out the other area so we can get that ultimate area that I initially shaded. Alright, so once we're able to extract this, then we're going to say, okay, well, now we know that we have some sort of function that we want to work with. So working with that function, and I'm going to write it here really quick. Working with that function, we now get the function of some radii is 1/2 r squared. All right, and typically this comes as the area of a sector from trig. All right, so area of a sector from trig, but now we're going to apply some calculus to it. Let's say that we take the derivative here. If we take the derivative, then we're left with 2 divided by 2 multiplied by r, and this is going to be dr, which naturally means we just get r dr. Now, in the spirit of calculus, let's go ahead and let's take a integral to undo this. Now you might be saying, well, we just took a derivative, why are we going to take an antiderivative? Well, we want to undo it, that way we can get back to where we're at. And where we're at is this one function of r is equal to the integral of r dr. And this is where we want to be at, because notice these two functions, the function with respect to the radius can be expressed in two different ways. And if it can be expressed in two different ways, that's going to be real nice, because I want you to observe this part right here. And let me see if I can choose a different color to show you that. Here we go. I'm going to go with purple. Notice what we have right in here. 1/2 r squared. 1/2 r squared is that function. But that function can be expressed as the integral of r dr, which will now be a natural sense for us to say that if we want to find the area of a sector in polar coordinates, yes, we are absolutely correct that it's going to go from alpha to beta, and it's going to be 1/2 r squared d theta. But if we express it using our newfound integral, this is going to be the integral from alpha to beta, then the most innermost integral is going to be the integral from a to b, and this is going to be r dr d theta. Now you might be saying, where is a and b coming from? A and b are coming from these initial radii. So we go back over here to our picture. So going back over here to the picture, drawing a little asterisk, and we're going to draw R1 is going to be A, R0 is going to be B. And therefore we're going to be able to get what we need here in order for us to be able to extract what is this particular integral going to evaluate to be. All right. Now, in general, oops, excuse me. Let me do this in blue. In general, when we want to look at double integrals in polar coordinates over some domain or over some region for some function with respect to some area, then if we're going to do this in polar coordinates, we have to find some function that is containing theta, and we need to make those substitutions into our function. Making these substitutions, we will be able to calculate what is our integral using polar coordinates. All right, and this is the most general formula that we want to use in this class. That when we're looking at double integrals in polar coordinates, we're going to be trying to identify, first of all, what is the domain. And typically, anytime that we want to look at the domain, anything that we can parameterize using polar coordinates. If we can parameterize using polar coordinates, then we want to go ahead and we want to use these double integrals set up in polar coordinates. All right, so it's going to be very important for us to observe the domain for these functions. All right, so now that we have the basics here, let's see if we can go through an example really quickly. So this example, we're going to evaluate by converting into polar coordinates. So here goes the first one, part A. The first one's going to be the double integral over the region D for 2xy with respect to some area. And then the domain or the region is the portion of the region between the circles of radius 2 and radius 5, centered at the origin that lies in quadrant 1. Alright, so here's a question that says, we have to evaluate this integral and we're given this domain. So because we're given this domain, that's the first thing that I want to focus on. Now, the really nice part about this is that we're given the domain, which is the portion of the circles that lie in quadrant 1. And these circles are centered at the origin. All right, so let's see. I'm going to be at the origin. Here's my first circle. I'm going to give this radius 5. And I'm going to give another radius. And this one's going to be radius 2. So there we are. We have our two circles. Now I'm going to go ahead and I'm going to shade the area that I want to observe here, or I want to integrate over. So this is the area that we want to integrate over here. And that's my domain. So let's see if we can go through and we can set this up. So the double integral over some domain for 2xy with respect to the area. Alright, we're going to have to go through the radii first. So the radii is going to be the innermost integral. So the radii that we're going to go through, or the radii that we're going to be sweeping through, I'm going to do this in orange here, is going to be this radii that I'm looking at, right? Or the difference between those two radii. So the difference between those two radii is going to be from 2 to 5. Nice. All right, and that's going to capture every single movement that we make here. Depending on what angle measurement we go through, it's going to give us all of these specific lengths. Now, the outermost integral, that's going to go between two angle measurements. So we now have to see what angle measurements are we sweeping through. So the angle measurements that we're sweeping through, right? We got to figure out what angles we're actually making. All right. So all of these radii are actually sweeping from 0. This was your 0 degrees or 0 radians, all the way to 90 degrees. But we'll do this in radians, which is pi halves. And now that we have this, we can actually go through and we can actually start setting up our integrand. The integrand is going to be 2 times x times y. So using 2 times x times y, we're going to go through and we're going to make our conversions. X under polar coordinates is r cosine theta. Y under polar coordinates, it's r sine theta. And then we have our constants of integration, dr d theta, or our differentials. So it's going to be important for us to see that these differentials always exist here within the change of base. We went from Cartesian over to polar, and we need to account for that when we look at that. Anytime that we look at dA with respect to the area in polar coordinates, that's always going to be r dr d theta. All right, so now that we have this, we can go through and we can simplify a few things here. All right, now before I integrate, I don't want to go ahead and jump into integration right away. I want to actually sit back and look at what I have. I have r cubed multiplied by 2 sine theta cosine theta, and that's going to be dr d theta. Now, looking at this particular integral, we can then say, all right, the integrand kind of looks like a double angle for sine, so I'm going to go ahead and make that substitution. All right, I think it'll help me out a little bit later. So it's going to be r to the power of 3, and this is going to be sine of 2 theta dr d theta. Now this integral here, we can go ahead and we can integrate r. Integrating r shouldn't be too bad. Whoa, excuse me for that. Nope, that's not going to help with the format. God bless you. All right, let's see. A little bit more, a little bit more, a little bit more, a little bit more, and there we are. Boom. All right. My apologies for that. This technology is driving me nuts. All right, so once we have this, let's go to r to the 4th. R to the 4th, this is going to be 1/4 r to the 4th, and this is sine of 2 theta. Now notice my dr's was the only item that I integrated. Theta was treated as a constant, or any function that has theta gets treated as a constant. And now that we have this, we can go through and we can start evaluating this integral using the r values that we just extracted. So this is going to be 0 to pi fourths. And now this is going to be, let's say, sine of 2 theta multiplied by 1/4 multiplied by 5 to the 4th minus 1/4 multiplied by 2 to the 4th. And this is all still with respect to theta. All right, so doing some quick calculations, we get 5 to the 4th, which is 625, and we're going to divide that by 4. And next we're going to subtract out 2 to the power of 4. That's 2 to the power of 4, and then we're going to divide that by 4, and we should get 609 divided by 4. So this is going to be 609 divided by 4 multiplied by sine of 2 theta. And this is all d theta. All right, so our job now is just to evaluate this integral. Now, I have no doubt in my mind that you can all do this, so I'm going to leave this integral evaluation to you. All right, what do we get here? All right, so if you want to take a minute to pause the video to see if you can evaluate this, awesome, go ahead and do so. But I went ahead and I gave you this answer just so you can make sure that you get the correct, or making sure that you're on the way to the correct answer. All right, so let's work on the next example. The next example, this is going to be part B. We're going to have the double integral over some domain for e to the power of x squared plus y squared. And this is all going to be with respect to some area. And we're going to say that D is the unit circle centered at the origin. Now, if this is going to be the case, then that's going to be kind of awesome for us. And the reason I say that is because looking at the domain is going to be really nice and straightforward to sketch. Here's x's, here's y's. And here's my unit circle centered at the origin. So the domain that I'm observing here is this domain here, what I'm shading in. So we then have to talk about this in terms of polar coordinates. So let's see how we're going to set this up using polar coordinates. Oops. Let's go ahead and make this a little bit more neat. E to the power of x squared plus y squared, and that's going to be with respect to dA. All right, let's see here. I'm going to work on my integrand first. X squared plus y squared. There's one thing that you should know about x squared plus y squared. Under polar coordinates, it is always equal to, you guessed it, r squared. Which means my exponent here is supposed to be my r squared value. Now all I have to do is find out what radii am I sweeping through, right? So the radii that we're sweeping through, the radii is always measured from that origin, the origin to that outer radius. All right, so as we're sweeping through this, look at all these radii that I'm drawing here. All of these radii go from 0 all the way out to this maximum radius of 1. Then the angle measurements. What angles are we sweeping through? In other words, what are those theta values? Those theta values, they begin at 0 and they end right back where they started at, but they did one full rotation, meaning they ended at 2 pi. Now, this is going to be really good for us because, again, at this point in time, we can now see, working with this, we're now going to have some integral to evaluate. Now, you got to be careful because, again, we went from Cartesian over to polar coordinates. So we need our differentials to match, which means we're going to have r, dr, d theta. Awesome. So now we want to evaluate this particular integral. All right, so let's go ahead and let's evaluate this integral. The innermost integral is going to go from 0 to 1. And I need to evaluate e to the r squared times r dr. All right, now one of the things that you can do here is working with this most inner integral. You can make a u substitution. If you make a u substitution, then you're naturally going to see that the integral that we see here is going to be e to the r squared. And let me see, taking that derivative, we multiply by 2, so we're going to have to divide by 2 here, and this is going to go from 0 to 1, and this is going to be d theta. All right, now we can double check this derivative. Double checking this derivative here, if we go ahead, this antiderivative, if we take the derivative, taking the derivative, we get e to the power of r squared, and then we take the derivative of the inside, the innermost function, which is r squared. The derivative of r squared is 2r. Multiply that by the initial derivative, 2's cancel, and you're just left with r. So this should be the derivative that we're looking for. These are not the droids you're looking for. All right, so here we go. Let's evaluate using r's. All right, so evaluating using r's here, this is going to be 1/2 e to the power of 1 minus 1/2 e to the power of 0, and this is d theta. All right, now naturally this is going to get us 1/2 e minus 1/2, and this is going to go from 0 to 2 pi. And this is d theta. Now I want you to observe here, as we go through this integral here, this integral, or this integrand, does not have any variables with respect to theta. Therefore, when we integrate, it's just going to be theta multiplied by the constants that we have here. And that's evaluated from 0 to 2 pi. That means that 2 pi is going to multiply my constants. Which means naturally we're left with pi multiplied by e minus 1. And there's the final answer. Not too bad, pretty straightforward. All right. Excuse me, I was cut off mid-thought. Okay, so what we're going to do now is we're going to keep working with these examples with polar coordinates, and we're going to develop more concrete, more harder examples. All right, so on this next example, here we go. All right, so next example. We want to determine the area of the region that lies inside R is equal to 3 plus 2 sine theta, and outside R is equal to 2. Alright, so what I want you to do is get a really quick sketch of what this looks like. Alright, so try to get a good sketch as to what this looks like. Now, I went ahead and graphed this on GeoGebra, and I have it on here. I first graphed the curve, the circle, which was radius 2, centered at 0, 0, and then I went through and I graphed 3 plus 2 sine theta. 3 plus 2 sine theta is here. And then what we want to see is this area, or this domain, being sketched out. Notice there's a little radii moving through, and we want that one to sketch out the domain. Now, just to make this a little bit more interesting, let's start a trace. So let's show that trace. Awesome. So this is the area that we're looking for here. All right, or sorry, this is the domain that we're looking for here. So trying to identify this domain and how we want to work with this domain, right? We first need to identify what are the bounds that we're going to be integrating. In other words, what theta values are we sweeping through? So that's the first thing that we need to do, is we need to identify what domain values we're going to have there. All right, so keeping this in mind, I'll come back to it. Here we go. Awesome. So let's see. We want to find the area. Now, according to our work, area that we find for these integrals, or for these double integrals, is going to be the double integral over some domain, or over that region, of only r dr d theta. And this was that first formula that we saw at the very beginning, right? At the very beginning, how we derived everything. So what we need to do really quickly is we need to find when these two curves intersect. So when do these curves intersect? Well, the two curves intersect when they are equal to one another. R is equal to 2 and R is equal to 3 plus 2 sine theta. Subtract the 3 over, that's going to be negative 1 is equal to 2 sine theta. Then that's negative 1/2 is equal to sine of theta. This will then tell us, naturally, according to the unit circle, there are two different theta values. Theta must be 7 pi 6 or 11 pi 6. So those are the two values that we need here. Now, I want you to look at this part right here. So let me see if I can move it on screen here. All right, this part here, this looks like that 11 pi 6, but there's an issue that if we're sweeping starting here to the left, we can't begin at 11 pi 6 because 11 pi 6 can't start off as a big number, 11 pi 6, and then start traversing and then go to a smaller number, which is 7 pi 6.
Did it work?
In other words, we have to re-index this 11 pi 6. So, theta values that we need. Definitely 7 pi 6 is one of them. But 11 pi 6, I want to think of it differently. Would you all agree that 11 pi 6 will give the same trigonometric outcome as negative pi 6? And it should, because those are coterminal angles, so we should be good. Alright, so here we go, setting this up. Double integral. Oops, sorry about that. Here we go, double integral. So the innermost integral is going to be the radii. What is the radii sweeping through? So when we look at this radii, where does it start? It starts here at the circle, and it goes all the way to this outer function. So it starts at the circle, goes out to the function. That means it starts at the circle, radius 2, and it goes out to the function 3 plus 2 sine theta. Angle measurements. Angle measurements go from negative pi 6 all the way to 7 pi 6. And this is going to be integrated with r dr d theta. So that's actually the hardest part here, setting up the integral. Setting up the integral while we're sketching the region. All right. Now, once we have this, we can just go through and we can solve. Now, I want you to actually take the time and solve. If you want to pause this video, go ahead and pause the video and go ahead and attempt to solve this. I'm looking for explicit answers, meaning answers that are not rounded. So this is going to be 11 root 3 over 2 plus 14 pi over 3. And that's the answer we want, or that's the answer I want. All right. So take some time, again, work on that integral and make sure that you get to this exact result. All right. Now, let's work on a different type of problem. All right, here goes. So on this example, we're going to have to evaluate the double integral over the region D for 1 plus 4x squared plus 4y squared. This is dA, where D is the bottom half of the circle. X squared plus y squared is equal to 16. So let's start by sketching that domain really quickly. The domain is the bottom half of the circle. Bottom half of the circle with radius 4. That means sketching wise, this is the region that we are observing. So sketching this region, that's awesome, we got it done. Now all we need to do is set up the integral. Now the reason why I always say sketch the domain first is because every time that you sketch the domain actually gives you insight as to what you should be using, whether you're going to be using polar coordinates or whether you're going to be using Cartesian. Since it's a circular domain, we want to use polar coordinates. So we're going to use all of our trigonometric substitutions to make sure that we get this correct. All right, so innermost integral. Innermost integral is going to go for radii. So what are the radii? And I'm drawing them here. Look at all of these radii. They begin at 0 and they end at 4. Theta. What angle are these sweeping through? The angles, they start at pi and they go over to 2 pi. And that's again because it's the bottom half of that circle. Now my substitutions, 1 plus, this is going to be 4 times r cosine theta squared plus 4 times r sine theta squared. And this is all going to be r dr d theta. Now, using the simplification for the integrand here, simplification for the integrand should get us something real nice. It should get us 1 plus 4r squared for that radicand multiplied by r dr d theta. And once you get here, you want to use a u substitution. You can do u is equal to 1 plus 4r squared, which means du will be 8r dr. And you can then make that substitution here. So the hardest part is now done. The next part that you have to do then is integrate this. So spend some time, go through the integration, or you can put pause here, go through the integration, and you will be able to get your answer. Again, I'm not looking for approximate answers, only explicit answers. So this one's going to be pi divided by 12 multiplied by 65 to the power of 3/2 minus 1. That's the final answer. Awesome. All right. So now that we have a little bit more experience with these integrals, let's see if we can take it up just a little bit more. All right. So here we go. Next example. So on this next example, oops, here we go. We want to use a double integral to determine the volume of the solid that is inside the cylinder x squared plus y squared is equal to 16. Below, z is equal to 2x squared plus 2y squared. And above, the xy plane. Wow, so we got a lot going on here. So it says use a double integral to determine the volume of the solid that is inside of the cylinder. So we want some volume that's inside of this cylinder, but below this particular paraboloid, which is z is equal to 2x squared plus 2y squared, and above the xy plane. Wow, awesome. So I want you to try to envision that just for a quick second. Right? Try to determine what it is that we're actually looking at here. Alright, so now that you've tried to envision this, see if we can go through and try to extract what we're looking at. So, again, with most of these visualizations, I have GeoGebra applets for them. This one can be found on the GeoGebra homepage that I have for us. So here's where I want to see to show the surfaces. So here we have a cylinder, which is denoted in red, which was that x squared plus y squared is equal to 16. And we have this paraboloid, which was given by the equation z is equal to 2x squared plus 2y squared. Now you're going to see that we want the volume that's inside of this cylinder, but that's outside, or in other words below this particular paraboloid. So below the green part, but inside of that red cylinder. So I want to click show volume. Alright, I went ahead and I've parameterized this so we can see what it is that we're looking at here. And I'm going to unclick those surfaces, and here we go. Now, you might say, hey, where's the top part for that intersection? Well, it doesn't really show it until you actually go and find that intersection. The intersection is actually going to be very, very large, a very large z value. All right, so you see they're up here, they're incrementing by 5s for z values. That means it should be somewhere way up here, so around 35, 40. All right, so we want the volume that's captured inside of the cylinder, but outside of that paraboloid, but still above the x and y plane. So we can see this figure that will get us some sort of volume here. And that's what we want to figure out. So let's look at this domain-wise. So domain-wise, here we go. We want to figure this out. So let's go through and let's start drawing this domain. All right. Now, what I want to see here is I want to see where this is going to be intersecting. All right. What's the largest amount of area that is being integrated over when we're looking at the x and y plane? Would you agree that the area that we're actually looking at is going to be defined by the cylinder of radius 4, like such? Now all of the area is going to be inside of the cylinder, and I keep talking about area because yes, we are looking at the area, and that area that we're integrating over is going to get us the base of this figure, but then we also need the height, but the height, we'll get to that in just a little bit. Alright, so domain wise, here we go. So we want this volume. This volume is going to be the double integral over some domain, and we need this to go to some sort of function. If we have the area, all we need is the volume. In other words, we need the height for all of these areas to attain. The height is going to be from the x and y plane, in other words, from z is equal to 0, all the way to some top height value. That top height value is going to be that paraboloid that we're integrating over. That's that paraboloid with respect to the area. So all we got to do now is convert all of this into polar coordinates. So let's go through that. We have 2. Would you agree that x squared plus y squared is just r squared? Alright, good. I would too. Alright, so I'm just going to keep this as a domain. Here we go. So making this 2r squared r dr d theta. Alright, we need radii. Radii goes from 0 to 4. And that radii that I am initially looking at is this radii beginning at the origin, going out to this specific value on the cylinder or on the circle. Always going to be from 0 to the radius. Alright, so now that I have this, alright, let's see. Here we go. Alright, so now that I have this, I need some sort of theta. What's the theta value that we're sweeping through? You guessed it, 0 to 2 pi. There we are. Which means all we have to do is integrate here. Now, this actually turns out to be a really, really nice integral. So I want you to take some time and go through the integral. And again, it should be a really, really nice integral to evaluate. So once we evaluate this integral, we should get 256 pi as our final answer. All right. Now, if you're still trying to envision this, it's okay. So one of the things that I try to do as well is not only do we want to look at them on GeoGebra, but we also want to sketch them out to see if we can get these figures to look like what we kind of envision in our minds, right? Because at the end of the day, we're in this business to make sure that we can get this visualization going for us. Alright, there we go. Going up in there. And that's going to come back out this way, that way. And in here, where we have these circles, concentric circles, there we are. So the volume's inside of there. Now, the initial height that I was looking for, the initial height went from the z-axis, from the x and y axis, all the way to this height here for that paraboloid. That was the height that I was looking for. That height was given by that 2x squared plus 2y squared. All right, so there's that type of visualization that we have, that we can still envision this even though we might not have the use of GeoGebra to use during an exam or anything like that, but we can still find those specific values, or we can still envision those specific regions. So that's going to wrap it up for today's video. So I hope you all enjoyed this, and I will see you for the next one.